rise, please. Please be seated. So, ladies and gentlemen, colleagues, friends and family of Maurits, welcome to Eindhoven University of Technology. It is a pleasure to have you here for the inaugural lecture of Professor Maurits Kaptein. For those who do not know me, my name is Edwin van den Heuvel, and I am the Dean of the Department of Mathematics and Computer Science and can play the role of rector for a short moment today. So today we celebrate not only Maurits' academic achievements, but also his ability to bridge the two worlds of science and entrepreneurship. Because he's not just a scholar, he is also an entrepreneur, co-founding and advising tech startups that translates academic insights into practical business solutions. This synergy between academia and industry is very powerful. A recent article in the Harvard Business Review highlights that one technique consistently boosts performance in startups: the scientific method. Startups that apply this centuries-old discipline of formulating, testing, and refining hypotheses outperform those that do not. They generate more revenue and pivot away from unviable ideas faster, crucial for every early-stage firm. Professor Sjoerd Romme, who is our TUE professor on entrepreneurship, has made the observation that the processes of entrepreneurship and scientific inquiry are strikingly similar. They both involve pioneering, exploring new territories, finding ways to make things happen, and addressing specific problems for targeted audiences. You might get back to that, I don't know. In Maurits, we see a person who embodies this spirit of discovery and application. Today, he will talk about his work and views on advanced statistical methods for sequential learning and causal inference. Maurits will address the lack of methods that can fully incorporate uncertainty present in both data and underlying causal structures. That's good, going well so far, good. The nice thing is that Maurits already knew his way around here in Eindhoven. He did his doctorate in industrial design at our university, graduating cum laude. That's why I'm so happy to welcome him back. After his PhD, Maurits worked at institutions such as Stanford University, Aalto School of Economics, Radboud University, and Tilburg University, further enriching his academic journey. With over 2 decades of research experience in artificial intelligence, machine learning, and statistics, Maurits has made significant contributions to the domain as diverse as online marketing and healthcare. He is the author of 4 books and over 100 peer-reviewed articles. But as I mentioned, Maurits has also made a name for himself outside academia. He co-founded the Scalable company, a Dutch deep tech startup specializing in edge AI, which was acquired by Network Optics earlier this year. He's currently chief data scientist at the company. Since 2023, we have had the privilege of calling him our own professor of applied causality. I'm so happy and proud to have him here, especially because Maurits is capable of fostering the collaboration between academia and industry through his innovative research. At the same time, this makes me just as happy. He is thinking about the next generation who need to focus on the challenges we face as a society. Maurits is a dedicated educator, teaching advanced analytics and AI and mentoring students and researchers at all levels. Maurits, your talent to combine cutting-edge research with real-world applications makes you the perfect person to unite knowledge from academia and practice. This combination of expertise has already led to great results, and I am convinced that it will be no different in the future. We are very happy that you have chosen Eindhoven University of Technology as the place to continue your impactful work. Knowing your drive and ambition, I have no doubt that you will find your way within and outside our university to boost your own research. I also hope we can continue our personal collaborations going forward, even though sometimes we have different views. I still recall our first meeting many years ago. We had to meet each other because we were both responsible for the first year statistics course in our joint bachelor program on data science with Tilburg University. I think we very quickly ended up in a kind of a heated discussion on statistics and causality, where you defended the Bayesian method or philosophy and I defended the frequentist philosophy. I already looked a little bit at your inaugural lecture, at a peak review, and I think we will look at some of the things differently again. But don't worry, I will not give the audience any spoilers. Although we sometimes see things differently, this has never prohibited us to work together, and we have always found common grounds to contribute to the statistical science. I appreciate our relationship and the respect we have for each other as a person and for our scientific work, and we both accept that we can have different views. This is how science works and should work. Maurits, on behalf of all our colleagues, I wish you great success in the years to come, and I am looking forward very much to your views here today and for the views for you in the future. Please give Maurits an applause and come up here.
Ooh. Well, thank you all for coming. It's hard to surpass such an introduction, I would say, so maybe we should go for drinks. Thank you for coming. Looking at this amazing title and amazing font, I think you are all pretty sure you're up for the most exciting 60 minutes of your life. It will be only 60 minutes of your life, so you'll get over it, basically. What I'm going to do today is talk a bit about the type of work that I hope to be doing in the coming years. I'll try to introduce it slowly and step by step, and I'll try to not make it too technical. There is a written version of this talk, there you go, and that contains a bit more technical details. So for those actually interested in some of the details, I've written them up, but I won't be actually talking about them. I want to start with a very simple question. It's the question, I wonder what happens when I press this specific button. So this button changed my slides, but we've all had this question before. If you, for example, have a new rental car, you try to press all the buttons and see what happens. Children like to press buttons and see what happens. And one of the interesting things about such questions is that they are what one would call causal questions. So basically these are questions that ask what actions have what specific effect. So if I press the button, does the light turn on? Yeah? So causal questions, a specific type of questions that I'm interested in. And you can see causal questions in science everywhere. Just as an example of a causal question that I have worked on with Gijs Gelijns, who's there in the back as far as I know, is a causal question on the effect of chemotherapy. This was adjuvant chemotherapy, so that's chemotherapy administered after surgery for colon cancer, and the effect of this action, so giving chemotherapy or not giving chemotherapy, on the survival rates of people. So that's another causal question that you can imagine we would be interested in. So we see causal questions everywhere, And some people might be tempted to think that causal questions are very simple to answer. I mean, you just press the button and see what happens, basically, or you give a number of people chemotherapy and you compare them to those that don't have chemotherapy. One of the tricky things, however, in actually answering causal questions is what is known as the fundamental problem of causal inference. What is the fundamental problem of causal inference? It's the simple idea that for one individual, I can never, at the same moment in time, under the same circumstances, see what would have happened if I've not treated them. So for example, even though I press the button and the light goes on, maybe the light also would have turned on if I hadn't pressed the button. We never really see those two, what's called counterfactuals, those two sides of it. So we always have to infer these things. We always have to think about how can we basically generalize from one to the other. And that's what I want to talk about today, and I want to talk about potentially new, I hope, new ways of looking at that problem. Before I do, though, I want to make it slightly more formal. I'm not going to be too formal in this talk, but I'm going to do a few of these. One slightly more formal idea is a black screen. That's coming back up every now and then. I was warned, by the way, by the technicians that this would happen every now and then. I don't know what the cause is of this, but apparently it happens every now and then. So we will be talking a bit about the average treatment effect. It's a name that's given for a very specific causal effect, although there might be more causal effects that one would study, but it's a very specific one that has a lot of interest. And it basically means what is the difference on average between a treated group, so those that actually get chemotherapy, and an untreated group, so those that do not get chemotherapy. So the average treatment effects, what is on average over the group, the effect of this treatment. And more mathematically, we often notate it something like this, and I'm not going to go into too many details of these things, but the basic idea is we have the outcome under the treatment on average, so Y is often denoted as the outcome. The 1 between brackets indicates the treatment, whereas the 1 between brackets on the right-hand side indicates not getting the treatment. So it's a difference between receiving the treatment and not receiving the treatment on average. No? Interestingly, for one specific person at one specific point in time, we never see both of them at the same time. And so that's kind of this fundamental to your problem of causal inference. So I hope that gave a bit of an idea of the types of questions that I want to address and the types of things that I want to talk about. And I will start talking about this by talking about creating models to answer such causal questions. Why will I talk about creating models? Because I would say one of the main kind of goals of science is to create models that help us answer questions. So what I'm going to do is try to address these types of causal questions that I've just introduced, but I'm going to take it very, very slowly. I'm going to start by what is a model to begin with, and then how do we learn models based on data, and then how do we actually get to answering some of these causal questions. And I'll end up, sorry to foreshadow that, with a model that's not yet finished. It's the model that I hope to work on in the future, but I'll try to motivate at least why I think it's useful to study these new types of models. See, everyone's super excited. So let's dig in. Let's dig in. So the first thing is creating scientific models. So what does it mean to create a scientific model? Scientists create models of the world or of systems or of things they try to understand. And one of the things that often happens is that people that are not super versed into kind of this model-making exercise are distracted by the complexity of the world when they're trying to make models. So it's useful to think about very simple systems if we want to think about what models actually are. So what I want to do is start from a very simple system that we're trying to model and then make it more and more complex as we go. No, Daniel, you cannot ask questions right now. So there's a very simple question, a very simple system here. It's a very simple machine. The machine works as follows. If I press the button on the top, it prints digits to a tape. Yeah? It is really not very impressive. I see people like, am I not understanding this? No, you're understanding it. It's a super simple system, a system that prints digits. And what I want to try to model is the inner workings of this machine. I want to understand, create a model of this machine. What does it mean to create a model of this machine? I would say it basically means that we have some way of generating answers to questions that you could ask about this machine. For example, what is the next digit that will be printed? Or will it ever print 10 zeros in a row? These types of questions are questions that we might ask, and we might want to make a model to answer such questions, partly based on the data that we see coming out of this machine. So let's press the button 10 times and get some data, basically. So here's just a bunch of zeros and one that we try to model. And now I want to be a bit more technical about what a model actually is. And I know that the definition for a model that I'm now going to give is, slightly, well, not controversial, but like, oh, there's many definitions of models throughout the sciences. So this is just one way of looking at what models are. I would say if we're trying to understand these data, we can create a model, and a model is composed of 4 different elements. Here they are. The first one is a set of assumptions. So models, and actually I would say pretty much all of science, start with assumptions about the world. We start with things that we generally believe. Sometimes we spell them out, sometimes regretfully we don't, but there's a set of assumptions that underlie pretty much every model. Then we often have some way of summarizing the data that we see. So in this case, it's all the zeros and ones. How do we summarize them? Do we mathematically summarize them in some ways? Then a model is often composed of update rules. Update rules meaning, what if we get new data? How does our model change? Sometimes we might change our assumptions based on new data, but there's some machinery for if we see new things happening, how do we potentially change our model? And finally, there's a set of answer rules. And not everyone is always used to thinking about these as separate things. So, for example, some of my colleagues are used to regression-type models, for example, and using specific parameters of those models to provide answers. But in some ways, that already is an answer rule, looking at all of you guys now. So we have a model. The regression model itself is the summary of our data, and the answer rules are whatever we use to answer the questions that are being asked. So that's a high-level, somewhat abstract description of a model. Let's turn off the screen, turn it back on, and then go for one specific example of a model. I hope it turns back on. Seems like it. There we go. So let's think about one specific model just for this data that we were looking at. And I'm going to call this model the parity of pi, so the even or oddness, even of oneven in Dutch. And I'm going to assume that this machine prints out the parity of pi. So for each digit of pi, p, prints out whether it's an even or an odd number. Admittedly, it's a weird assumption to make, but there would be more scientific models that make weird assumptions as a start. It's a weird assumption, but it's one that we can follow through. So basically, it kind of looks like this. So I have these zeros and ones, and I have pi mapped underneath. So there's zeros for all the odd numbers, ones for all the even numbers. It's a model. It's my assumption about what this machine is doing. It's printing out the parity of pi. Well, if that's the case, then it's super simple to summarize my data. After 10 digits, I'm at the 10th digit. That's all I need to know. If I get more data, I can simply just update this counter. And interestingly, if you ask me, are there ever 10 ones in this sequence, we kind of know how to compute pi. Actually, it's still pretty active research topic for the amazingly large numbers, but we kind of know how to compute pi, so we know how to answer a number of these types of questions. Yeah? Bit of a ridiculous model, but it's an example of a model. Specific assumptions, ways of learning from data, updating, and answering questions. Okay? There we go. Now, given that we now have seen one, this slide's intentionally left blank, by the way. Given that we have seen one example of a model, it's good to kind of think about these different types of models that we could have made for this machine. And I think one thing that is useful to note is the fact that if we have different models meaning different assumptions, potentially different data summaries, but if they all provide the same answers, it's going to be very hard for us to tell them apart. So if we have two different models, which maybe are motivated in a very, very different way, so with a very different set of assumptions, as long as they provide the same answers, it's going to be hard for us to tell them apart. And because of that, I would be tempted to say, personal opinion, that a lot of science, where such models are made, is not necessarily pursuing what some people believe is the truth. I would argue, we actually create models that are useful. They're useful in answering questions, but at some point we're never able to really check whether all of our assumptions were correct. And hence, what we're trying to do is just create things that usefully, meaningfully answer questions. And maybe we're trying to get better at it, but we're not necessarily getting to the objective truth, whatever that might mean. So we're just trying to make models that are useful. Interestingly, though, if the models provide different answers, then we can empirically check them. So we can see on future data whether one of those models performs better by some metric, as like how good was the answer, basically. So there is a way of advancing science. There is a way of advancing methods, or there's a way of advancing models given new data. But the way I would look at it, they're never really true. They're just useful in making potential predictions. Now, it would be very funny if at the end of this lecture I actually get to the root cause of this blackout, but I won't. It was there you go. So that's a bit of a background about models. The parity of pi model obviously was only there to kind of illustrate the type of thinking. I hope that was clear. What I will talk about more in this lecture are what are called probabilistic models, statistical models. These are specific types of models that allow us to deal with uncertain events. So you could think about these zeros and ones as just a sequence of, well, I don't really know what's happening. There might be a sequence of, the heads and tails of a coin that one tosses. Joris, I'm going to slip in coin tosses in every talk that I do. So you toss a coin. If it's heads, it's a 1. If it's tails, it's a 0. And we're trying to kind of model that type of behavior, basically. Well, that's something that, there's a few technical details, but basically it's something that we call a Bernoulli random variable. Effectively, we're just going to model this data, these zeros and ones, as originating by tossing a coin. The coin, however, might be biased, meaning like one side might be heavier than the other side, so it turns out heads more than half of the time, for example. Well, how often does it turn out heads? Well, this is kind of our data summary, and the standard way of doing this, although there's multiple ways that you can motivate, but a standard way of doing this is looking at this data, seeing how many ones there are, and so it's 3 ones out of 10. So what I'm going to just deduce from this data is there's a 3/10 probability of landing heads. Now, 7/10 of landing tails. That's my model. So now I have theta. That's just our common way of denoting this one parameter that we use to summarize this data, which is just the probability of heads in this case. Hope that was still cool. The moment we get new data, we can recompute data. So there is a way of actually computing kind of a new summary for this model. And interestingly, and this is somewhat by assumption, and now we have to get back to the power of some of these assumptions. By assumption, this model has been studied a lot. And due to the study of this model, we can actually answer a whole lot of questions about this specific model very, very easily. So it's very easy for us to compute, for example, what is the probability of throwing 10 ones in a row. Daniel? How much? No, you're like, yeah. No, it's extremely small. So it's 3/10 to the power of 10, basically. So it's extremely small, but these kind of things we know how to do because we're assuming something that other people have assumed before, that mathematicians have studied, so we can build upon this knowledge. Yeah, it's our modeling exercise. Okay, so I hope by now I've given you some idea of building models of a simple system. I know it's only zeros and ones, it's a really simple system yet, but we're trying to get to these causal questions. We'll get there in 20 minutes or so. It'll take a bit of time, my apologies, but we'll get there. We'll get to these causal questions. But I hope, at the very least, it's shaped some of how we're thinking about what it means for science to model or understand a specific system. From here, one thing that I want to note, and it's particularly useful because at some point I'll be talking about slightly more complex models, we can actually often summarize models visually. And this is, I know, a very stupid summary, because it's just a number line from 0 to 1, and the 3/10 is where the tick is. So it's just a one-dimensional thing, because our data summary was just one number. This is a way in which we could visualize the data summary of this specific model. Not all too impressive, but as we go and make more complex models, it's useful to have visualizations. Okay? Is everyone still on par? See some nods, thank you. Let me eyeball the time of where we're going. Okay, still there. So I want to extend these models to modeling uncertainty in specific ways. And just to kind of get into that topic, the model that we just created, as I said, is useful. It builds on a lot of theory. There's a lot of specific answers that we can give based on that model. But one of the things that that model does, if I'm just summarizing the data by this one specific number, is that it kind of gets us into a situation where if the data is like the top of this or the bottom of this, that in both cases, and these are somewhat contrived, we have 3 out of 10 ones, or 15 out of 50, so 3 out of 10 ones. So I have these two very different data sets. And in some ways, this model that I was just looking at, which in some ways has been some of my discussions with Edwin as well, the model that we were just looking at will give effectively the same answer, because it computes the same quantity for both of these data sets, which is a bit tricky because these are very different situations. If I press a button many times and always the same time happens, at least intuitively, we kind of feel we're getting more certain about the effect of the action that we do. So that's something I think we want to include in our models. And to include this in our models, we can think about changing some of the modeling assumptions that we have in our background. So what I'm trying to do is take this very simple model that provides reasonable answers for just these zeros and ones. However, it doesn't include this notion of gaining more certainty as we gain more data, which at least is something that we intuitively all, I think, have some notion for. So how do we actually change that? Well, we can change it into something, and now I'm gonna think, I've written out some of these things in much more detail, even with code. You can download it, play around with it. I'm gonna skim it at a somewhat higher level in this talk, but we can make what's called a Bayesian model. And a Bayesian model here, just kind of for the sake of argument here, would be a very similar model in the sense that we would still think about modeling a coin, basically, that we're tossing. However, now this one quantity, theta, so the probability of heads, is itself uncertain, and it's something we are trying to learn based on data. The way we do this, one way of thinking about this, is that we extend this model to not just have as a summary one number, but two numbers. Effectively, these relate one-on-one to the number of heads and number of tails, but they give us a slightly more flexible number, basically. And they give us a screen that stops. So this is just one extension of a different set of assumptions that allows us to model this data in a different way, for which a lot of properties are, again, known. So we can answer questions based on this model. Now it's getting a bit tricky, what's happening right here. But we can answer questions based on this model and effectively, hence, model the uncertainty in the data more properly. I would say more properly. And the interesting thing is, as we've just established, models are subjective based on the assumptions. So I can just say, I like this model more, I like these types of models more, I like Bayesian models more. So my future work will be more in this direction, effectively. Let's summarize this data set a bit. So now the summary is a bit more involved. It's not one number, it's two numbers. And what you're looking at here is effectively of all the probabilities of A1 or a heads, so from 0 to 1, how likely these are by kind of the height of this little plot. You can also see my drawing skills, and I'm happy I didn't go into drawing. Anyway, drawing on the left-hand side, what this model would give us is basically the idea that, well, 3/10 is the most likely probability of turning on heads, but there is quite some probability, or it's quite likely that it's much higher or much lower, because I've only seen a few observations. So I'm not yet very sure about the probability of heads. Whereas the graph on the right shows how this would evolve if you have these 50 observations. So if I have more data, and what you can see, it's more narrow. So basically what I'm saying now, I'm more convinced that it's actually 3/10, and a value like 9 out of 10 is very, very unlikely by this time, given the data that I've seen. So you can see how this data, or how this model behaves slightly differently than the previous data, and how it behaves slightly differently as you get new data. Okay? Great. So by now I've introduced this silly machine that if you press it, like a 0 or a 1 comes out. I've tried to introduce models by virtue of assumptions, summaries of data, ways of updating that summary, and ways of providing answers, basically. And I've taken you all the way through towards my preference for what I would call Bayesian models. But I think for the purpose of this talk right now, mainly it's just types of models that, given their assumptions and their machinery, allow you to include all the uncertainty that you have about the amount of data, basically driven by the amount of data that you get, to include that in your modeling exercise and into the answers that you give. Interestingly, model 2, so this one theta model, and model 3, the last model that I just showed, this Bayesian model, actually do provide different answers in some different cases, so you can even potentially tell them apart in specific situations. So they're really distinct two different models. Okay? We're very far from our causal question where the chemotherapy causes you to live longer, but we'll get there at some point. We need to extend a bit more. So I'm going to extend our models, or first extend the system that we're trying to model. And here's my second machine. It's not amazingly exciting yet, but if you press it, now it prints 2 digits at the same time. Yeah? So it prints a combination of 0, 1 or 1, 0. And now this is the device that we try to model. And just to kind of clarify, this is the type of data that comes out of this machine. Every time I press it, it basically gives you a tuple or a pair of a 0 and a 1. Yeah? Now, interestingly, the type of model that I've just introduced, so this Bayesian model, can easily be extended towards what's called a multivariate case. So when we're concerned with multiple variables, the way of thinking about this is the first row of ones is one variable, the second row is another variable, basically, and we're interested in how those 2 variables, every time you print them, relate to each other. All of this machinery already exists. Actually, together with Professor Dr. Mulder, who's right there, one of our PhD students, Cynthia Kavelaar, has developed or worked on specifically these models. How do we understand the interaction between these 2 binary, so just 0 and 1 variables? And this is the kind of papers that she wrote. Let's not go into any of those. But effectively, these types of models exist, and we can summarize them again. And interestingly, this is a very different type of summary, so I'm trying to visually summarize it again. But now this is a much more complex model. It doesn't just have 2 parameters, it has 4 in this case. One way of summarizing it is by a plot that somewhat looks like this, and this is what one would call an altitude plot, hoogtekaart. So if you're looking like from the top on a mountain, you could say, well, the probability of y, so that's the second row, the lower row, 2 out of 10, that is given by how high this mountain is on the plot, how much to the left or the right is kind of the probability of the x, and the mountain will get steeper and steeper the more data I get. Hope that was still there. Cool. Okay, so that is just extending this model to more to what's called multivariate data. And interestingly, as I said, this model, so we started out with this very simple machine, 0s and 1s. Now we have tuples of 0s and 1s. Even that model, so this specific Bayesian model that we did, you can think of specific answer rules based on this summary. And one of the studies that we were involved in at some point was trying to model the effects of brain radiation therapy for people that had a tumor in their brain. And there's 2 potential outcome measures that people were interested in, namely after the radiation, do people decline cognitively, or does the tumor reappear, basically? So we had 2 outcome measures, cognitive decline and the reappearance of the tumor. And we used exactly this type of Bayesian model to model how for a set of individuals, so each individual had a tuple, cognitive decline, and yes or no reemergence of the tumor, for a set of those individuals, to model how this behaved, so how the effects were of this treatment. And she developed new answer rules to make decisions to, in the end, decide whether or not the treatment was favorable, yes or no. So even this model, and we'll get into some of the more causal details in a second, but even this simple model has actually found its way into practical use, into clinical practice. Okay, so we started super simple, adding bits, and already getting to things that are somewhat useful, but not yet to this causal question that I started with. So let's move over to that one. And let's start by thinking about, we had this simple machine. How can we alter this machine to provide data that is meaningful? If I'm thinking about what happens when I press the button, I know that pressing the button prints the digits. Oh, it's a bit tricky in this whole setup. But what happens if I actively intervene with one of these digits? How do I model a system like that? So how do I model, for example, subscribing chemotherapy to people and then seeing the results of what happens? Yeah? Well, we could envision a machine like this, and this is where my drawing skills really stand out, a machine like this, where the first row is again zeros and ones, the second row is again zeros and ones, printed whenever you press the button, but there's two switches. And if you play around with this machine a bit, if the switch is set to 0, so on the top row, the switch is set to 0, it always prints zeros on the top row. If it's set to 1, it always prints 1 on the top row. And if it's set to void, this, great, this circle with the stripe through it, then it prints kind of seemingly randomly zeros and ones. So it's back to kind of the type of behavior that we were looking at before. So now I've changed this machine to include these two switches, and effectively the first switch sets the upper digit, and if it's set to 0, it always prints a 0. Yeah? Is that a reasonable construction of the machine? Cool. Then it gets us to this type of data, which tricky to see. Neat. Well, there we go. Yay. So basically, one way of denoting the data that now comes out of this machine, these zeros and ones, is what I'm using here is to subscript them with how the switches were set. So subscript 1 will always print a 1, basically. A subscript 0 will always print a 0. Void, the subscript with the dash through it, can print any of these things. So this is the type of data that now I get. Again, it's representative of this new machine that's printing this new type of data. It's a bit contrived, perhaps. However, if you think about it, it is potentially a useful analogy for the types of causal questions that we ask ourselves. So what I've tried to do by introducing these models or these machines is to focus our thinking away from like the complexities of the world to just the core of the problem that we're trying to study. And if you think about this machine with these two levers, you can actually map it somewhat by analogy to this problem of understanding what the effects are of chemotherapy on survival rates. I know this is a stretch for some people. But you can think about this data as basically saying the first digit, so the top row, basically, is whether or not individual people, so each row is a person, the first, or each column is a person, the first row is a bunch of data. The first row meaning, did people receive chemotherapy, yes or no, 0 or 1. The second row, did they survive for 5 years, 0 or 1. And it's persons for every column. Yeah, so this is kind of this type of data I can map partly to this causal problem. And what do the zeros and ones mean, the subscripts? Well, the ones mean I subscribed chemotherapy to somebody. Yeah, so somebody came into the doctor's office and I gave them chemotherapy. The zeros mean we didn't give them chemotherapy. The voids mean we received data, but we don't really know. So somebody has gotten chemotherapy, yes or no, but we don't really know how it came about. Like, we didn't set the switch actively, we didn't actively intervene, somebody just came in, or we just received this data and it happened to contain chemotherapy, yes or no. It's kind of an interesting thing because if you talk with people that manage the Dutch Cancer Registry, I think a few of them are there in the back row, what they actually have is a lot of data with people that have treatments or don't have treatments, but they don't really know in some cases, why the treatment was given or what the mechanism was for this 0 or 1. So basically, we're setting apart actively intervening versus just observing what happens. Okay? It's very annoying that this thing keeps going off, but there we go. So now, given this new machine, I can try to map it back to this average treatment effect that I talked about in the beginning. So now I want to know what's the difference between actively intervening on the first switch, and what's the difference when I set it to 0 in the average outcome of y to when I set it to 1 in the average outcome of y. which is kind of the question that we try to answer. What is the difference between actively giving people chemotherapy or actively not giving people chemotherapy? There we go, back up. So we were just looking at this average treatment effect as a difference, like y brackets 1, y brackets 0. I can now make it slightly more precise because we're actually looking at, well, what happens to y? So for this specific, again, think about it as just a person, when I specifically give them chemotherapy or when I don't give them chemotherapy. So that's kind of the thing we're interested in. Yeah? I hope this somewhat worked. I'm trying to like step by step get to this like causal problem. Now we have like causal data at least, and now I'm trying to say like, oh, this is the thing that we're trying, one of the potential questions we're trying to answer. What is the average treatment effect? And we can now define it a bit more because it's basically what is on average the outcomes of these, the lower row, given that I set x to 1 or given that I set x to 0. Okay? So let's think about how we can model this, how we can model this new system and how we can potentially answer this question. I did warn you beforehand it was not going to be the most exciting hour of your life, but we'll get there. So how do you get to understanding these causal machines? Interestingly, there is 2 ways. I think Edwin would say at least 2 ways, but interestingly, there's 2 interesting ways of kind of understanding or modeling these types of machines. One of them is actually very simple by the way we set it up, and it basically means, well, if I want to estimate this average treatment effect, so the difference in outcome of y when x is set to 1 or when x is set to 0, well, as long as I just know the data generating mechanism, so if I know how the switch was set, if I know why people received chemotherapy or didn't receive chemotherapy, it's relatively easy. I just compute this difference only on that subset of data. So if I have a lot of data where for some people, if I map it back to the chemotherapy case, I know exactly why they received chemotherapy. I was in control of administering it. For some I don't, I was in control of administering it. And some data, basically I got from a colleague in a different hospital, I don't know what happened, well, I'll just ignore that data. Basically, I only look at the data for which I know exactly how the data was generated. And under relatively mild assumptions, so there's a few more tricks that go into this, you can actually compute this average treatment effect by just computing the difference between those 2 groups, as long as you know how the data was generated. I hope that made some sense. I want to stress a bit more that this difference actually occurs quite a lot, that we know or do not know how the data was generated, and that there's pros and cons of these different things. So if we just look at healthcare data, for example, today, we do see in hospitals that people have been treated or have not been treated, but often we don't really know how this exactly came about. Maybe there was some rule involved, but maybe the doctor didn't necessarily follow that rule, which is very different from us actively manipulating, like administering some specific drug, chemotherapy, yes or no, and looking at the data that comes out of those 2 things. So what basically, the moment we really know how the treatment was chosen, we can compare these 2 groups. If we don't, it becomes pretty fast, it becomes pretty tricky. And I just want to show you why this becomes tricky and what the actual differences are in practice, just to get some feel. There's a bit more machinery behind it. But what if we don't know how the switches were set, basically, in the data that we're looking at? Well, there's, I think, a very intuitive example out there in the world. It's the intuitive example if you look at the treatment of breast cancer for, regretfully, mostly females. If you look at chemotherapy being subscribed to females with breast cancer, and you just look at chemotherapy, yes or no, and the 5-year survival rate, what you'll find if you just get random data is that the survival rate is lower for those that receive chemotherapy. So if you're just looking at data coming from the field, you don't know why chemotherapy was subscribed, you get the effect of chemotherapy is actually negative. Yeah? Now, in reality, what happens is that the tumor size, and it's a bit more involved, but I think the easiest way of explaining it is just the tumor size affects whether or not it's easy to surgically remove the tumor. If it is easy to surgically remove the tumor, we don't need chemotherapy. Whereas if that's hard, because it's a severe tumor or it's a big tumor, then it's likely that some malign cells remain, and with this, oh, we have to combat these cells with chemotherapy. So basically, you receive chemotherapy if you have a severe tumor, and survival rates are lower if you have a severe tumor. So if we're just looking at this data in the field, we might conflate causation with correlation. We might conflate the effects of chemotherapy by those both being caused by this common cause, the tumor size. If we really want to know just the difference between these two, we would randomly administer chemotherapy to some, randomly not administer chemotherapy to some, and basically break the reliance on chemotherapy. So that's one way of getting to causal effects, is understanding how the treatments were administered, being in control of those. It gets you to what's called the randomized control trial. There's a lot more kind of machinery involved, but that's one way of getting to causal effects, provides you with valid causal effects. It is just one way, and I said there's two ways, at least two ways of getting to this causal effects, and luckily that's the case, because one of the tricky things is we have a lot of causal questions in this world for which we're not going to actively intervene. For example, if we want to know if smoking is bad for people, that's something that at some point was actually a question. It's very hard to take half of you and make you smoke for the next 10 years. We now have similar problems with vaping, pesticides, all of it. There's all of these things that we will not be actively intervening. We'll just get data of some people that started to vape and some that didn't. And we might compare their outcomes, but we're always stuck in this potential problem because we weren't setting the switches ourselves. So what is the second way of actually getting to a proper estimate of this average treatment effect if I wasn't intervening? So can I still use some of that data, basically? Well, there is a solution to it. The solution is actually fairly obvious if you're thinking about this machine, and it's what would be called knowing the causal structure that underlies the problem. If I go back to my machine, it's very simple. If I know how it's wired, so if I'm thinking from left to right on the machine, so I press the button, if I first generate X, so the top row, and that affects Y, okay, fine. Now, if I know that this is the actual causal structure, now it doesn't really matter how the switches were set or whether I'm actively intervening. By having this understanding of the problem, of how this data is generated, I can now use virtually all of the data, irrespective of how the switch on X was set, to estimate the causal effect. So if I can't control it, if I understand how it's wired, I can still compute this outcome. And so that's another way of computing it. This has been an active literature for the last a bit over a decade. I'm really understanding how these structures are and maybe how we learn them. And it's nice because once we are certain that this is a structure, we can do something like this. So we can use all the data when the switch was set to 1 and also when it was set to void, basically. So now we can use more of this data. Yeah? It's nice. It's nice. It's also tricky because if that's the case and we were wrong in our underlying structure, our answers will be totally wrong, basically. So we will effectively confuse causation for correlation for causation. Okay, so what I've tried to do is set up this scheme of getting to understanding causal effects, focusing on just what does this data actually look like, and getting to two potential ways of understanding these effects. One is actively manipulating, setting the switches. The other one is understanding how these machines actually work, so understanding how the wires work. So maybe understanding the biological processes of how chemotherapy actually works. If we know all of these things, potentially we can provide some answers. So those are two ways of understanding causal effects. And slightly more abstractly, we often think about the inner wirings of these machines. We often think about these, what's called graphs, directed acyclic graphs. So it's just arrows between X, the top row, and Y, the second row. Does one affect the other? Or maybe there's a common cause, like the severity of the tumor that we just saw. So we can make these types of structures. If by now you're bored, you can start thinking about how many of these structures, so one arrow one way, one the other way, there are as a function of the number of variables. So here it's on the right side, it's X and Y. On the left-hand side, I've introduced U as well as a third variable. But if you just think about how many possibilities there are, again, if you're bored, I'll get back to that at some point. But this is a way in which we think about these underlying structures that are there. Now, we know that we can estimate causal effects, so we can make models that work if we either know how the switches were set or if we know this underlying causal structure. And I hope to have motivated why both of these, at least at somewhat high level, why both of these approaches potentially work, to give you a proper answer to what's the effect of this action that I'm taking. What is tricky, however, is right now, these two approaches come from pretty differing schools of thought. And if you think about the ways we're currently modeling these types of things, we often potentially include some of the uncertainty about like how many observations that we have. That's why we chose Bayesian models. But we often don't include the uncertainty that comes from our uncertainty in setting the switches or our uncertainty about these different causal structures. There's a lot of literature on how do we decide which causal structure is true, but often, given a causal structure, we proceed, and we don't really include the uncertainty over these causal structures into the causal models that we build. So what I want to do in the next few years, what I want to build on and study is new causal models. And these causal models, I think, should collect a number of the pieces that I've talked about right now. So they should be able to answer causal questions. For example, answer what's the average treatment effect. These models should have proper assumptions, so it should be clear what all the assumptions are. They should have data summaries that work, update rules. If we see new data, how do we learn from new data, and how do we answer specific questions? So for example, how do we compute this average treatment effect? I think we should use probabilistic models, and more specifically, I think we should use Bayesian models to include the uncertainty that arises from our sampling. However, I think we should also embrace models that include both this knowledge of the data-generating mechanism, so how were the switches set, as well as the underlying causal structure. So what I try to do is start from a very simple system, this first machine, extend it to a machine that kind of maps to a more meaningful question, the simplest of all causal questions, namely what's the average treatment effect, what happens if I administer chemotherapy to you guys and not administer to you guys, and how do I take all of those bits into a meaningful model that allows us to answer causal questions, either using the underlying causal structure or knowledge of how the data was generated. So I want to build these types of models, and now things become a bit fuzzy because this is hopefully the things I'll be working on for the next few years. But what I want to work on is what I'm going to try and call, because every now and then you have to coin a name, compound causal models, models that include basically all of the bits that we've just talked about. And those models, I think they should basically assume, if we're just looking at this binary case again, we can use this Bayesian model that I've just introduced that was used for like the cognitive decline, like that summary of the data. We can use it as one of the components of the model, but we extend it by having some idea of what is the causal structure underlying all of this. And effectively, to summarize our data, we use the models that we've just looked at, namely what's the relationship like between these zeros and ones, these two Bayesian models that we looked at, and we also include some notion of which causal structure is most probable. Now, if we want to throw all of these things into a model, luckily we're at a point that a number of things about this are already known. So in some ways, if we assume one specific data-generating mechanism or one specific causal structure, we know how to update all of these things. We know how to provide answers. That's where the state of the literature is right now. What we don't know is how these things really interact. We don't really know if, for example, if I have way more variables, and for some of them I know how they were generated, for some of them I know the causal structure, how those assumptions can be interchanged, basically, to compute things. That's a field. There's a lot of open questions there. There's more open questions for example, quantifying how probable each of these potential causal structures was. So I gave you this two variables with one arrow between them, but if you have more of these things, how do we actually quantify in a proper Bayesian way so that we actually learn from new observations which of these causal structures is most likely? We also don't really know how to include that knowledge into computing the answers. So there's loads of questions. It's tricky, huh? Sorry, we just got to this point. You can wonder, okay, why are we doing all of this? So why did I set up all of this machinery, get to these models that by now are what are we talking about? We're including all of these different bits and stuff. Well, obviously, this is what I'll be working on for the next few years. But I think right now, the reason to pursue this is not because I already know it's going to give better answers or that any of this is really going to work. But if you think about one very specific situation, it's a very simple situation where you have a lot of data. You don't know how the switches were set. So basically, you get data just from a hospital of people being treated with chemotherapy, yes or no, whether or not those people survived, yes or no. And you don't really know what the causal structure was. So there's uncertainty in how the data came about and uncertainty about the causal structure. This is surprisingly common. The way I'm trying to set up these models, if you would use those, and again, there's ways of actually computing them in the actual written out version of this, you would get an answer to this question of what's the average treatment effect that looks as follows. We're going to average over all of the potential causal structures, and we're going to get to an answer that looks like this, which isn't a very appealing answer. It is not a very appealing answer, but it would quantify that there is some potential effect. So if you get chemotherapy, there might be a probability that you live longer. So that's the little blob on the right. Depending on how much data I have, that blob might be more narrow or more wide. However, there's also going to be quite substantial, which is what's called a point mass, a quite substantial mass at 0. Why? Because, well, maybe if chemotherapy is not causing the outcome, but there's some common cause, then the effect will be 0. And since I don't know which of these things was true, I should incorporate this uncertainty into the actual answer that I compute. This is not an easy answer, but it's the most fair answer that we can give based on all the data that we have at that point in time. So that's why I think basically quantifying both what we think is the effect based on the data and quantifying our uncertainty about the causal structure in the answers that we give, I think that's providing the most fair answer of what we as scientists can model based on the data that we have, and hence these things could be combined. Well, almost wrapping up. Thank you. Thanks for hanging in there. Not too many people left during the talk, just one, so that's fine. I hope to have introduced a bit how we actually can work on data from very simple systems to systems that kind of get to this causal question. I hope to have taught you at least about this fundamental problem of causal inference. We never really see what would have happened if we had done something else. Various ways of dealing with that. So one way of dealing with that is actively intervening ourselves. The other one is understanding the structure. And I would like to be able to combine all of these things to provide valid answers. That's what I hope to be working on the next few years. There's a few challenges, though. One challenge is this thing that I just asked you about how many of these potential structures are there, given a specific number of variables. Anyone is willing to guess, if you have 5 variables, whether there's more or less than 100 of these structures. Audience participation is always great. So raise your hand if there's more than 100 if you have 5 of these variables. Okay, more than 1,000? Oh, you know probably. So how many are there? A lot, close to 30,000 actually, which is amazing. So it's amazingly quick growth of all, because it's all the potential arrows, non-arrows, all the subgraphs. So really, if I want to include all of this structure into these models will become very complex. Here's a little plot of the number of possible of these graphs as a function of the number of nodes. So that's something we have to deal with, provides cool computational challenges. Another challenge, though, which I think is much more the core of what I'm trying to do in this talk, is that right now, the general audience, on that side of the room, I guess, the general audience likes to ask questions to scientists. For example, does chemotherapy work? And we all prefer very simple answers to those questions. We prefer yes or no. Yes, it will make you live for another 12 months. And because we prefer all of that, scientists are also tempted to give these kind of answers. Scientists are tempted to say, we provide the truth, we say what is actually correct, so we're going to just say 12 as the effect in months of chemotherapy. However, if we look at what we actually know based on the data that we have and the assumptions, I think we should be a bit more honest. We should be honest that a lot of these assumptions we're uncertain about, that our data is limited, so that there's a lot of uncertainty that goes into this 12. And maybe we should not say 12, maybe we should say somewhere between 10 and 14, but there's also a probability that it's 0, because we don't really understand what's happening underneath. And I think, both on this side of the room and on this side of the room, we should all embrace this uncertainty, because I think that's the most valid answer that we can give based on the knowledge that we have at that moment in time. So that was this kind of introduction to what it means to build on causal models and the types of models that I hope to work on. And by now, I hope to also be at a point, I know it's kind of tricky, it took an hour, to get to a point where you understand the title, because I got a lot of feedback from people like, wait, what is this title? So this title means uncertainty propagation, so it means taking uncertainty that comes from the sampling, the data generating mechanism, the causal structure, propagating it, so taking it forward, including it, into causal effects estimation, so into our computations of this, for example, average treatment effect. So that wraps up my talk. Thank you guys very much, and now it's, I think, time for drinks. Or you got to stay seated for a while, by the way. Thank you.